In this video, we are going to have some special classes of rings with examples. First, we have the first special class is integral domain, for which we need the definition of zero divisor of a ring. If R is a commutative ring, then a non-zero element A in R is a zero divisor of R if there is a non-zero element B in R such that AB is 0. We don't have both A and B to be 0, but the product gives us 0. Now, for example, if we consider AZ6 under addition modulus 6, multiplication modulus 6, we know that this forms a commutative ring. And in that, if we consider class 2 with class 3, if we multiply this multiplication modulus 6, then we know that it is class 6, but Z6 in Z6 class 6 is nothing but class 0. The remainder when 6 is divided by 6 gives us 0, and that is why we have 0 here. And similarly, if we consider 4 and 3, 12 that we get, and 12 on division by 6 leaves the remainder 0. 12 on division by 6 leaves the remainder 0. So you get your class 4 multiplication modulus 6, class 3 also to be 0. So class 2, class 3, class 4, these are all zero divisors of Z6. We say that an element, non-zero element, to be a zero divisor if there exists another non-zero element such that the product gives me 0. So for 2 we have 3, and for 3 we have 2 as well as 4. So we don't have these, we have these to be zero divisors. Now the ring of integers is a commutative ring without zero divisors, because you don't have any non-zero elements A and B in Z such that A be 0. If you want to have the product to be 0, you need to have either A or B to be 0. So ring of integers, that is, we have seen already that Z under plus and dot, it forms a ring. This is an example for a commutative ring, we have said already. So in this, we don't have two elements, non-zero elements, whose product gives us 0. So this is a ring without zero divisors. Now comes the definition of integral domain. A commutative ring without zero divisors. It should not have zero divisors. Then it is called an integral domain. So if we consider A dot B 0, we should either have A to be 0 or B to be 0. That is what is called as an integral domain. We should have this implying either A 0 or B 0. This is called an integral domain. Right. Now we have one lemma which states that if R is a ring with A dot 0, we are going to prove that A into 0 is 0, and similarly 0 into A is 0 for every A in R, and A into minus B is minus AB equals minus AB, and minus A into minus B is AB. If R has unit element, minus 1 into A is minus A, then minus 1 into minus 1 is 1. See, so far we have been using this in lower classes, but the reason behind that, why we write that, that is given in this lemma. Now you consider the first one, A into 0. The 0 can be rewritten as 0 plus 0. And by distributive law, we have this to be A into 0 plus A into 0 again. So whenever you have A plus B giving you back A, means whatever you have in a ring, this is nothing but the additive identity present in the ring. So we have in this ring 0 to be the additive identity. So here what we see, the 0 is the 0 element, or rather additive identity of this ring R. So we must have a plus b giving back a means this must be additive identity. So here you have a0 plus a0 giving back a0. So this a0 should be the additive identity. And similarly we can establish that 0 into a is 0. You can similarly write the 0 as 0 plus 0 into a, and by distributive law you can have it as 0a plus 0 into a. So we have 0a being rewritten in this way, 0a plus 0 into a. Again 0 into a plus 0 into a giving back 0 into a. So whatever here I have should be the additive identity. So you have 0 into a to be 0. So you have a0 also to be 0, 0a also to be 0, where 0 is the additive identity of the ring R. And coming to the next one, ab plus a into minus b. When we consider by distributive law, this is nothing but a into b plus of minus b, but this is nothing but 0. Just now we proved that a into 0 is 0. So you have this to be 0. And so this in turn tells that whatever here we have, see again this concept, whenever you have a plus b giving you 0 means whatever here you have should be the additive identity, which is written in this way. So here you have a into b plus a into minus b giving you 0. So that means whatever here we have a into minus b must be the additive inverse. So it is additive inverse of ab. So which we denote as minus ab. And the same way for the other one also we have. So we have both minus a into b, a into minus b giving minus ab. So for this you can again consider 0 into b you can have, and that you rewrite as a plus of minus a b, use distributive law. So a dot b plus minus a dot b giving you 0 dot b, by this is nothing but 0. So you have this again same concept, whatever here I have, because this is 0 and whatever we have here should be the additive inverse of this. So we have this. Now if R has unit element, then this is what we are trying to prove. So you can make use of this minus 1 into b giving you minus 1 into b. So it has unit element means it will be just b itself. So instead of b you have a. And in this, when you replace a by minus 1, minus of minus 1, a inverse the whole inverse is a inverse the whole inverse is a itself. So whether you are considering the additive part of it or multiplicative part of it, a inverse the whole inverse is a. But here we don't have R to be are having multiplicative inverse for all the elements. So we can make use of this. See, had it been asked in a field, then inverse of inverse is again the same element. So in that way we could have argued. But here it is not a ring. So I mean it is not a field. So we'll have to prove with the help of this only. Here you have mentioned that a inverse the whole inverse is a, but in this case you are having minus ab. When you consider this minus of ab, with regard to addition it is true. With regard to addition it is true. See, when you have a in this is with regard to addition, we have to understand that. Because not as under multiplication we cannot say this because it's not a field. So it is with regard to addition that minus of AB is AB itself. So this one minus 1 into a, you have this. So again this one a equal to b equal to 1. If you take in the third one, you get this. Now next one, every field is an integral domain. Let F be a field. Then F is a commutative ring with unit element. That's the definition. And all the non-zero elements have inverse in F. To prove that F is an integral domain, we have to prove that for AB equal to 0, we have either A0 or B0. Now we'll consider AB to be 0. Suppose A is non-zero, then A inverse should exist because F is a field. So pre-multiplying both sides by A inverse, this is what we get. And this is nothing but 1. You can use associativity. So you have this to be 1 into B, but 1 into B is B. Because F has unit element, so B is equal to 0. So if you don't have A to be 0, you need to have B to be 0. And similarly, if you don't have B to be 0, B inverse will exist, so you get A to be 0. So A dot B equal to 0 should imply either A 0 or B 0. So you have, that's the condition required for an integral domain. So every field is an integral domain, but we don't have every integral domain to be a field. Example for that is the set of integers under addition, usual addition and multiplication of integers. This is not a field because when you consider any non-zero element A, its inverse will be 1 by A. Its inverse will be 1 by A, which is not present in Z. Only for A equal to 1 and minus 1. You have the inverse existing, not for the rest. For example, if you consider 2 or 3 or anything, 1 by 2, 1 by 3, they are not present in a set. So it is not a group under multiplication, so it cannot be a field. But when can we have that integral domain to be a field? When it's finite, then you can have it to be a field. So that is what is established in this lemma. Every finite integral domain is a field. So we will consider D to be the given integral domain with finite number of elements, say x1 to xn with distinct elements. That is, xi is different from xj. For I not equal to j, we shall name this statement as statement P. Now D is a commutative ring because by the definition of integral domain, it has to have, it should be a commutative ring without zero divisors. Now to prove that D is a field, we have to prove that D, every non-zero element in D, has unit element. Every non-zero element should have inverse. D should have unit element in the sense that when we multiply any element A in D, we should have A into 1 is equal to A equal to 1 into A because commutative holds. It's enough we established this. So D has unit element we have to establish. Then having established a unit element, we have to show that the non-zero elements has inverse. So non-zero element has inverse, that needs to be established. That is the second part. Now we consider a non-zero element A in D. Then because D is a ring, we have to have x1a closure hold. So x1a, x2a and so on xna should be in D. Now we claim that these elements are also distinct. We know that these elements are distinct. Now we claim that when we multiply each one by A, then also it is distinct. Suppose not. Suppose you have xia to be equal to xja for I not equal to j. Then taking this to the left side, this is what we have, and by distributive law this can be written, and this in turn gives us xi minus xj equal to 0. Why? Because A is non-zero and D has no zero divisors. So no zero divisors means whenever you have A dot B equal to 0, that should imply either A0 or B0. Whenever A dot B is 0, you should have either A0 or B0. So here we have xi minus xj A to be 0 with A not equal to 0. And therefore we should have xi to be equal to xi minus xj 0, which in turn gives xi equals xj with I not equal to j. But that's a contradiction. I not equal to j we have been considering from the beginning. So here in this statement P we have said that these two are distinct for I not equal to j, but here we are getting they are equal. So that contradiction tells us that these elements are also distinct. Next, we are going to make use of pigeonhole principle, which states that if n objects are distributed over m places, then some place must receive two objects. Equivalently, if n objects are distributed over n places, then each place must receive exactly one object. See, suppose we have three places. We have three places, say, and we have three places, four objects. Then you will first place one object here, and another object. So three objects, three places over. Then you are left with one more. So either you will put it here or here or here. So if you have n, that is, this is more and this is less, means some will receive. On the other hand, suppose I have only three places and only three objects. Three places and three objects. Then in that case, each one will receive only, exactly one. So if n objects are to be placed over n places, they are to be placed in n places. So three objects, three places means each will receive only one. So by the above principle, already we have the holes to be this x1, from x1 to xn. You imagine them to be the holes. So you have x1 to xn you have. So imagine them to be the holes, and now that you are putting the objects x1a, x2a, and you are putting them there. So that means each one will exactly receive only one object. So that is why we have xia to be equal to xj. Now since a belongs to D, a itself can be written in this way. So we shall write it as to differentiate xi naught, x suffix I naught a. Commutativity holds, so we can have this. Now you consider B to be any arbitrary element in D. Then B again can be written as xka, x suffix ka. Now we will claim that this xi naught serves as our identity element. So for which we need to establish that B xi naught gives me B back. So for that we consider B into xi naught. So that gives me B is replaced by xka. So you have this. And by this, associativity, we have this axi naught. So axi naught is nothing but a. So you have this. But xka is nothing but b by our assumption. So b xi naught is b, which means xi naught act as the unit element. For convenience sake, we shall name it as 1, so that we have xi naught to be 1. Now again, 1 itself being a member of D, 1 should be written as some xla. So rename again, just to have this one in a nice form, you rename this xi or xl, whatever it is, as some c, so that you have 1 equal to ca equal to ac. So that gives AC is also 1, CA is also 1 because D is commutative. So from these two, this is what we have, and that shows that C has inverse. So two things that we have established, that existence of unit element and existence of inverse also. So now we have a corollary to this lemma, or rather theorem or lemma, whatever it is. So we have established that every finite integral domain is a field. Now we want to prove that this collection of all congruence classes modulo P, which we either denote as ZP or JP. We have to prove that this is a field under addition modulo P, multiplication modulo P. Now, if we have to make use of this, we have to show that it's an integral domain. We have pretty well, we have our ZP consisting of finite number of elements. And we have the operations addition modulo P and multiplication modulo P. It should be a commutative ring first. And then it should be an integral domain for which zero divisors are not there. We have to establish. Then automatically by the previous lemma, the result will follow. So JP forms a commutative ring, needs to be established. If this is asked in section C, you'll have to consider the elements and mention all the axioms for it to be a commutative ring, and the previous lemma is also to be proved. As such, if you consider the proof of this corollary, in few steps it will get over. But all these are to be established. It forms a commutative ring under addition modulo P and multiplication modulo P. And of course, class 1 is the unit element. So, by the previous lemma, it is enough we prove that. So, 8 axioms are to be proved. 8 axioms are to be proved. See, for a field, remember this, for a field, actually we need 11 axioms. What are they? 5 axioms with regard to addition, namely closure, associativity, existence of identity, existence of inverse, commutativity. And similarly with respect to multiplication, 5 more. Closure, associativity, existence of identity, existence of inverse, commutativity with respect to multiplication. And then distributive law. So this one way we establish field with these 11 axioms in this way. Another method is it should be a ring, which means 8 axioms are needed. 8 axioms for a ring. Closure, associativity, existence of identity, existence of inverse, commutativity with respect to plus, and closure, associativity. So 6, 7, distributive law 8. So 8 axioms for a ring. And then we'll have to consider the existence of unit element, and non-zero element should have inverse. Non-zero element should have inverse, and we have to have commutativity. A dot B should be equal to B dot A for every AB in this. So there are 2 ways by which you can have your given collection to be a field under these 2 operations. So here we follow this one. So it's a ring, but neither of this is considered. See, neither this is considered nor this is considered in this case. Instead, then what is considered? It's a finite integral domain. So without zero divisors, if you are able to establish, then being a finite integral domain, it will be a field. So neither this technique nor this technique is used, but field, the previous lemma is used, for which first we have to establish that this ZP or JP under addition modulo P, multiplication modulo P is an integral domain. So it has no zero divisors. So that is what is established here. You consider 2 members, class A, class B. The product is 0. We have to show that either this is 0 or this is 0. Now if you consider this, we have this one implying class AB equal to class 0. So equivalence classes are equal means the elements must be related. And how the relation is defined? It is congruence modulo P. So we have this. So by the definition of congruence modulo N in general, we have this implying that P divides AB minus 0, which means P divides AB. But P being a prime number, P must divide A or P must divide B. This is rewritten this way. So, and this is rewritten in this way. And this in turn gives A is congruent to 0 mod P and R B congruent to 0 mod P. Which means A is related to, so straight away we can have A related to 0 or B related to 0. We have either A related to 0 or B related to 0. This need not be given. And whenever by the property of equivalence class, A related to B implies and implied by class A equals class B. So using that we have this class A to be 0 or class B to be 0. So JP has no 0 divisors. So it is a finite integral domain and therefore it forms a field. Next we have an integral domain R is said to be of characteristic 0 if for A not equal to 0 the relation MA equal to 0 holds only if M is 0. Now in the case of integers it's an integral domain of characteristic 0 because whenever you consider MA to be 0 you can have this to be 0 only if M is 0 with A not equal to 0. So A should not be 0 and the relation holds only if this is 0. But on the other hand, if you consider is 7, when we consider, we don't have class 1 to be 0, even 7 to be 0, but 7 times class 1, which means class 1 is added 7 times, gives us class 0. So neither this is 0 nor that is 0, but the product gives us 0. So in such case, we call this to be a finite characteristic. So an integral domain R is said to be a finite characteristic if for A not equal to 0 there exists a positive integer M such that MA is 0. An integral domain R is said to be of characteristic N if N is the least positive integer for which NA is 0. See here 7 into class 1 is 0, 14 into class 1 is also 0 and 21 into class 1 is also 0 and so on. But of all them 7 is the least. So this is the characteristic of Z7. Now if an integral domain R is of characteristic N, then N must be a prime number. This is one of the results. Whenever we talk about finite characteristic of an integral domain, not for a ring but for an integral domain, we speak about this, must be a prime number. Let R be of characteristic N, then by the definition N is the least positive integer such that NA equal to 0. So you have N to be the least positive integer for which NA is 0. This NA is 0. Now our claim is N is a prime number. Suppose it is a composite number. Then N equals N1 into N2 with N1 less than N, N2 less than N. Now we have NA to be 0. So replacing N by N1, N2, we have this. Now for B not equal to 0, we have obviously this 0 into B giving back 0. This is what we have. Now we shall have this to be N1A, N2B equal to 0. So this we have this is proved in one of the problems. Now we have N1A to be 0 or N2B to be 0 because R is an integral domain. And this is a contradiction to statement P, which states that N1 is less than N and N2 is less than N. And here NA is 0 with N to be the least. You cannot have any other number which is less than N satisfying this. That's what statement P says. So from here you have N1 to be less than N, N2 less than N along with this. So that's a contradiction and therefore our N cannot be a composite number. It should be a prime number. And one more point to be mentioned here, that it is integral domain, that part that we have used, that we wanted to mention every x here. On this point, if I got to mention that in this, you may think that we can use cancellation law and write this step directly. That cannot be done, because under multiplication it is not a group. It's only an integral domain. So it is not a group. Only if it is a group, you can say that you can have right cancellation law and you have this step directly, this one directly. But here it is an integral domain, so it has to be discussed in this way only. Okay. So thank you.